Hello, my name is Nur Aida binti Lutfi.
And my name is Muhammad Fidas Badullah.
My name is Rifana Suha.
My name is Azul Akmal bin Arizam.
And this is our leader,
And we are from
FEDORA
Freya Group.
Today, I would like to explain about background of the virtual memory management. First, in the virtual memory, code need to be in memory to execute, but entire program is not needed in many cases. The error code usually routine, some error seldom. If ever occur in practice, this code is almost never executed. On top of that, large data structure such as array. This and table are often allocate more memory than they actually need. For example, an array may be declared 100 multiply 100 element. If the top is seldom larger than 10 multiply 10. Second, consider ability to execute partially loaded program. The program no longer constrained by limit of physical memory. Program can be written with an extremely large virtual memory address, simplifying the program tasks. Each user program could take less physical memory, more program could be run at the same time, which increases CPU utilization and throughput. Meanwhile, less I/O would be needed to load or swap user program into physical memory, so each user program will run faster. What is virtual memory? Virtual memory is separation of user logical memory from physical memory. Only part of the program needs to be in memory for execution. Furthermore, the logical address space can therefore be much larger than physical address space. It allows address space to be shared by several processes. For instance, system libraries can be shared by several processes. It allows for more efficient process creation, as page can be shared during process creation, thus speeding up the process creation. More programs running concurrently, which means this I/O need to load or swap processes. Personal memory can be implemented by demand packing and demand segmentation. Next is about virtual address space. In virtual address space, heap can grow upward in memory as it uses the in dynamic memory allocation, and stack can grow downward in memory through successive function calls. The large blank space or hole between the heap and stack in part of the virtual address space but will require actual physical page only if the heap or stack grow. It could bring entire process into memory at no time or bring a page into memory only when it's needed. Less I/O needed, no unnecessary I/O. Less memory need, faster response, more user to be run page is need. Referring to it, the valid reference about now in memory, bring to memory. Next is lazy swapper. A lazy swapper is never split a page into memory unless the page will be needed. In the context of a demand packing system, use of term swapper is technically incorrect. A swapper manipulates entire processor, whereas a pager is concerned with the individual page of a process. We thus use pager rather than swapper in connection with demand packing. In page fault, if there is a reference to a page, first reference to that page will track to operating system. Page fault. First, operating system looks at another table to decide which is a valid reference and about, also just not in memory. Second, get empty frame. Third, swap page into frame via should this operation. Fourth, reset table to indicate page now in memory set. Validation bit. Fifth, restart the instruction that caused the page fault. Performance of demand paging. There are a couple of stages in demand paging. First, set to the operating system. Second, set the user register and process state. Third, determine that the interrupt was a page fault. Fourth, Check that the page reference was legal and determine the location of the page of the disk. Fifth, issue a read from the disk to a free frame in physical memory, which is 1. Wait a queue for the device until the request is serviced. 2. Wait for the device seat and or flexi time. 3. Begin the transfer of the page to a free frame. 6. While waiting, allocate the CPU to some of the user. 7. Receive and interrupt from the disk I/O subsystem. 8. Save the register and process state for the other user. 9. Determine that the interrupt was from the disk. Correct the page. 10. Correct the page table and other table to show page is now in memory. 11. Wait for the CPU to be allocated to this process again. Next is about copy and write. Copy and write allow both parent and child process to infinitely share the same page in memory. If either process modify a shared page, only then is the page copy. Copy and write also allow more efficient process creation as only modified page are copied. Free page are allocated from a pool of 0 out page.
In basic page replacement, first, you need to find the location of the desired page on disk. Second, find a free frame. If there is a free frame, use it. If there is no free frame, use a page replacement algorithm. And third, read the desired page into the newly free frame. Update the page and frame tables. And lastly, the fourth, restart the process. In Bilade anomaly, for some page replacement algorithm, the page fault may increase as the number of allocated frames increase. Next is about LRU page replacement. The important thing in LRU page replacement is time. FIFO use the time when a page was brought into memory. OBT use the time when a page is to be used. LRU, this recently use the time that a page has not been used. In LRU, replace the page that has not been used for the longest period of time, like OGP, looking backward in time. It requires hardware support for implementing LRU. In LRU page replacement, there is two possible implementation. First, counters. Whenever a page is referenced, the CPU clock counter is copied to the time of use field of the page. The page with the smallest time value will be replaced. Second step, whenever a page is referenced, it is removed from the stack and put on the top. The bottom page will be replaced, and together with OPT, they belong to stack algorithm that never exhibit the anomaly. A stack algorithm is the one that the set of the page in memory of n frame is always a subset of page in memory n plus 1 frames. LRU page replacement need less hardware support than LRU. Difference bit. First, with each page associate a bit initially equal to 0. Second, when page is referenced, bit set to 1. Third, replace the one which is 0 if one exists. We do not know the order, however, second set or clock need reference bit clock replacement. If page to be replaced in clock order have reference bit 1, set reference bit 0. Leave page in memory. Replace next page in clock order subject to same rules. Next is about enhanced second sense algorithm. Each page has reference bit, modified bit. Bits are set when page is referenced, modified. Page are classified. First, 0, 0, not referenced, not modified. Second, 0, 1, not referenced but modified. Third, 1, 0, referenced, not modified. And fourth, 1, 1, referenced and modified. Scan the circular queue and replace the first page from lowest number non-empty class. May scan the circular queue several times. And lastly, counting algorithm. Keep a counter of number of references that have been made to each page. LFU algorithm. Replace page with smallest count. MFU algorithm. Based on the argument that the page with the smallest count was probably just brought in has yet to be used. Neither MFU or LFU is common. The implementation is expensive and do not approximate OPT well. And lastly, my topic is about allocation of frames. How exactly to allocate the fixed amount of frame memory among various processes. Each process needs minimum number of pages, which is, example, IBM 376. 6 pages to handle SS move instruction. Instruction is 6 bytes, might span 2 pages. 2 pages to handle from and 2 pages to handle to. There are two major allocation schemes. Fixed allocation equals size or proportional to process size due to a priority allocation, and high priority process may have more memory. And last but not least, local versus global allocation. Local. Each process can select from its own set of allocated frames. And global, a process can select replacement frame from all frames. Even it is currently allocated to other process, has better throughput. Performance of a process depends not only on the paging behavior of the process but also on other process. A process cannot control its own page problem.
Hi, today I would like to explain about caching. If a process cannot maintain its minimum required number of frames, then it must be swapped out, freeing up frames for other processes. This is an intermediate level of CPU scheduling. A process that is spending more time paging than executing is said to be thrashing. Cause of thrashing. Early process scheduling scheme would control the level of multiprogramming allowed based on CPU utilization, adding in more processes when CPU utilization was low. Local patch replacement policies can prevent one thrashing process from taking patch away from other process, but it still tends to clog up the input-output queue, thereby slowing down any other process that need to do even a little bit of paging or any other input-output for the matter. To prevent thrashing, we must provide processes with as many frames. The locality model notes that processes typically access memory reference in a given locality, making lots of reference to the same general area of memory before moving periodically to a new locality. The working set model is based on the concept of locality and defines a working set window of length data. Whatever patches are included in the most recent data patch reference are said to be in the processor's working set window and comprise its current working set. A more direct approach is to recognize that what we really want to control is the page file rate, and to allocate frames based on this directly measurable value. If the page file rate exceeds a certain upper bound, then the process needs more frames. And if it is below a given lower bound, then it can afford to give up some of its frames to other processes. Next, I will explain about memory map files. Rather than accessing data files directly via the file system with every file access, data files can be patched into memory the same as process files, resulting in much faster access, except of course when patch faults occur. This is known as memory mapping a file. Basically, a file is mapped to an address range within a process virtual address space, and then patch is needed using the ordinary demand paging system. Windows implement shared memory using shared memory map files involving three basic steps. First, create a file, producing a handle to the new file. Second, name of the file as a shared object, producing a handle to the shared object. I would like to explain about allocating kernel memory. Kernel memory is often allocated from a free memory pool different from the list for ordinary user process. The kernel requests memory for data structure of varying size, some of which are less than a page in size. As a result, the kernel must use memory conservatively and attempt to minimize fragmentation and require contiguous memory. There are two strategies for managing free memory for kernel process. Number one is buddy system. Buddy system allocate memory from a fixed size segment consisting of physically contiguous page. Memory is allocated from the segment using a power of 2 allocator, which is satisfy request in unit size as a power and run up to the next highest power of 2. Next is slab allocation. A slab is made up of one or more physically contiguous pages. A cache consists of one or more slabs. Each cache is filled with objects that are instantiation of the kernel data structure. When cache created, it's filled with object marked as free, and when structure stored, the object marked as used. There are other considerations. One is pre-paging. Pre-paging is an attempt to prevent this high level of initial paging and to reduce the large number of page faults that are occur and process startup. Page size is to reduce the table fragmentation for larger page and internal fragmentation for smaller page. Page size selection must take into consideration number one is fragmentation, table size, input-output, and locality. Next is small page size. There is an advantage for small page size. Number one is less internal fragmentation, then better fit for various data structure code section, and then less unused program in memory. There is a disadvantage for small page size. Number one is program need many pages. Second, larger page program. TLB reach is the amount of memory accessible for the TLB, and simplify the number of entries multiplied by the page. Increasing TLB reach is to increase the page size. This may lead to an increase in fragmentation as not all applications require a larger page size. Then provide multiple page size. This allows applications that require larger page size the opportunity to use them without an increase in fragmentation. Next is input and output interlock. Page must sometimes be locked into memory. A process is doing input-output and has some page for buffer. Then, after issuing input-output, the process will be suspended while the input-output device is transferring data to buffer. A page for input-output buffer may be replaced by other processes via global allocation.
So we chose Museum Pendidikan Nasional as our place for shooting. And lastly, we want to thank you to everyone, especially to Syed Ismail, our lecturer. Thank you everyone. Yeah, gitu.
would like to explain. Ni apa? Explain apa? Explain off. 1, 2, 3.
Meanwhile, optimal pace replacement. Optimal pace replacement in Nanti kena buang.
Mi tak gurau Mi. Mi tak gurau Mi. Invaded reference and about. Just not in memory, get empty frame. Ish,
Apa ni? Apa kata ni? For LRU pace replacement, first is
kau dah lama. Aku fikir sampai 4. Sorry.
Share object to visual memory and which has its selection must take into
Sat.